Hi, my name is Krishna Maran, and this is Physics 2212 Lab 3. So for this lab, the purpose was to measure magnetic fields created by a bar magnet at various distances to find its path independence. So to do this, we used a magnetometer app on our phone, and we had a bar magnet and calculated the magnetic field by the phone from the bar magnet at various distances. So the formulas we used for this lab were the magnetic field of the bar is equal to K times R to the n being a negative number, and then the Biot-Savart law, which is the formula for a magnetic field, which is mu naught over 4 pi times 1 over r cubed, all times 3 times the dot product of mu times r hat minus mu. And then we also use the magnetic field of a dipole on axis, which is mu naught over 4 pi times 2 mu over r cubed. And as you can see, we put this formula in the code as well when we defined the formula for a dipole, and we calculate the magnetic field with that for the rest of the lab. And then the calculation we got for mu of the magnet was 3.825, and we will discuss how we got that later on in the lab. Average distance for each calculation of the magnetic field in the x direction that we had to do, and with that we created a graph, and as you can see in the graph, the slope is a negative 2.7816, which becomes our n. And since kr to the n is equal to the formula for the magnetic dipole on axis, the r to the n will cancel out with the r cubed, since negative 2.7816 is essentially negative 3, then therefore k will equal mu naught over 4 pi times 2 mu, and we have ln k because ln k would be the y-intercept, which is negative 15.573, and using that we find that k is 1.724 times 10 to the negative 7th. Therefore, with that, we can plug in k into mu naught over 4 pi times 2 mu, and we found mu to be 3.825 am squared. Now, to continue my data, for the off-axis field, we measured the magnetic field on the x and the y and the z-axis from the phone, and we also found the corrected measurement of the y so that the net magnetic field would be 1 times 10 to the negative 4th Tesla. So by doing this from the lab, we got the B net from the 45 degrees to be 4.94 times 10 to the negative 5th, 1.2 times 10 to the negative 5th, negative 5.1 times 10 to the negative 5th Tesla. But with the code, we got a much different answer from the distance d, which was negative 0.02, 8.96 times 10 to the negative 4th, 0, which is obviously the more accurate answer, since in the actual lab, there are lots of other things affecting the magnetic field of the phone, including human error. Now for the code. For the code, we first had to find the 2 on-axis locations of the magnetic field and the 4 perpendicular locations of the magnetic field. So for the on-axis locations, it was the observation axis 1 and 2, and we essentially just plugged in the formula from the dipole. We did the scale divided by 2 just so the arrows could be seen, and these were in orange and red. And then for the perpendicular magnetic fields, it was the observation locations 1 through 4 of the perpendicular locations, and we plugged in the magnetic moment and the observation location into the dipole formula shown in the earlier slide, and the scale is multiplied by 0.75 just so the arrows can be seen in the cyan color. Next, we found the net magnetic field with the 45-degree calculation, with the observation location being at the perpendicular distance of the x and the y, which is 0.16 found from our lab. And then we plugged in that location for the dipole formula earlier, along with the magnetic moment, and did that times 0.8 just so the magenta color arrow could be seen. Now for the discussion questions. What if we hadn't oriented our experiment to compensate for the magnetic north and had instead laid out our meter stick at some intermediate angle with respect to Earth's magnetic field? How would your results have changed? So the measurements would be off because we would be unable to determine which portion of the net magnetic field was due to the bar magnet and which was due to the Earth. Then the next question, what if you were to stick two identical magnets together end to end and run the experiment again? How would our measurements differ? Well, the magnetic field would be a lot stronger and the distances measured would be a lot smaller.